Hello everyone, I'm Hamid Fatemi Langerudi, research fellow at UTSA. Today I will be presenting a 10 framework to leverage the benefit of tapered fixed point for tinyML models on the tiny edge. One of the challenges in deploying the DNN on the edge is their model complexity, such as model sizes and number of operations. These models need to be deployed on ultra-resource constrained tiny edge devices that usually use microcontroller as a processing unit, which even has less computation capability in comparison to the model processor. To address this challenge, the DNN compressor models were proposed with various approaches. One of these techniques is low precision arithmetic using fixed point numerical formats. However, reducing the bit precision in fixed point numerical formats can jeopardize the model performance due to the limited dynamic range and uniform distribution as represented in the figure on the right. The plausible solution to overcome the performance loss with minimal hardware complexity overhead is the new numerical format, tapered fixed one, called tapered in the reference. We propose 10 empirical framework to emulate ML inference with quantization using the low precision tapered fixed point format. Moreover, we design a custom hardware architecture to study the latency and energy consumption of tapered fixed point compared to a standard fixed point. The tapered fixed point has two characteristics, variable dynamic range and tapered precision, as shown in this figure for 5-bit tapered fixed point. By modifying the IS parameter, the tapered fixed point can represent uniform and non-uniform distributions. The tapered fixed point uses two parameters, IS as a maximum number of bits to represent the integer part and is unit encoded, and SC as a scaling factor. For example, a number represented here in 8-bit tapered fixed point with IS equal 8 and SC equal 0 is 3875. To evaluate the efficacy of tapered fixed point format for tinyML model, we develop a 10 framework where at the first step, the numerical format parameters IS and SC selected to best represent the layer-wise dynamic range and distribution of parameter for tinyML model. We use the dynamic range of the tinyML model parameters in each layer as a metric for this selection. After this step, the weights and activation in 32-bit floats are quantized to the low-precision tapered fixed point format, upon which the exact dot product operation and activation function are then carried out. To study the hardware metrics such as latency and energy consumption of tapered fixed point compared to a standard fixed point, we modify the existing DNN accelerator IRIS version 2 with customized tapered fixed point, exact MAC unit with configurable bit precision. The encoding process the accumulated value and convert the integer value to unary format. The decoding process utilizes a counting leading zero a unit representing the integer value of the fixed point as shown in these figures. We tested the efficacy of this numerical format on various benchmark and data set. We observed that in all cases, the performance of tapered fixed point is better than fixed point for post-training quantization scenario. And we plan to compare this numerical format with other fixed point formats and other quantization approaches such as quantization award training. We analyzed the performance of tapered fixed point format on hardware and compare it with the fixed point. Overall, the hardware complexity of fixed point MAC operation is less than tapered fixed point format MAC operation. However, we also analyzed the performance of the tapered fixed point accelerator by simulating ResNet-18 model for classifying cipher-10 dataset on custom architecture. Tapered fixed one has shown better accuracy, energy delay product trade-off in comparison with fixed one. These references are used in this presentation. To conclude, we propose a novel tapered fixed point quantization algorithm that has the ability to adopt its dynamic range to match with DNN parameters, and we develop a new low precision deep learning framework 10 to demonstrate the performance of the tinyML model with tapered fixed one for classification tasks. And finally, we design a custom hardware architecture to implement 10 to study the latency, area, energy consumption of tapered fixed point compared to a standard fixed point. In the image classification task, the tapered fixed point would perform the fixed point with comparable hardware complexity.
Okay. Do you require any special training, or this is just a post-training quantization scheme?
This is for post training. We didn't do any special things. So, but we also tested quantization training, which is also we train in the train network and also used for the inference. So, but this is all for post quantization training.
Have you tried more challenging data sets, such as ImageNet?
Not yet, but we plan to do that.
So what about comparing to real fancy methods, such as some of those binarized method, binarized neural net, which obviously will require pre-training. So you are doing totally in post-training quantization. So what's the kind of starting neural net you require to have? You start with 8-bit or start with something for floating point, maybe?
Yes. Right. So we have started with 32 float when we learn the weights, and then we quantize to 8 bits, 7 bit, and up to 5 bit, and see the result. Yeah.
Can you go even lower than 5 bits?
Yes, but still we need to improve the accuracy. Still, for 4 bits, the accuracy is not as good as 8 bits. So might be that quantization error training is helpful in this case, or other uniform quantization and scaling, because scaling here is just for weights. Might be adding a scaling for activation also helpful for 4 bits.
No, there's a whole bunch of methods people are using nowadays. They use a group-based quantization. Instead of quantize each individual number, you quantize a group of values together. So you have a better opportunity to achieve a lower bit width. Yeah, there's a, for example, you look at Microsoft's brainwave, that kind of thing. They use group block floating point.
Right. So here is in the layer wise, but we can also have in the group wise, as you suggested, to improve the accuracy.
Yeah. Okay. Thank you very much.
Again, just a quick shout out to our sponsors. Bear with me for 1 minute. We have different categories. We have executive sponsors. First one being ARM. Then we have Qualcomm. We have Samsung. Platinum sponsors. Ada Compute. Lattice Semiconductor. Gold sponsors. BrainChip. Babel Labs. DSP Group. Edge Impulse. EMSA. Gray Matter Labs, Green Waves, HiMax, Imagimob, Latent AI, Maxim Integrated, Quixo, Reality AI, SensiML, Silicon Labs, Sentient, Google TensorFlow, XMOS, and lastly, silver sponsors, Edge Cortex, Hotchi, and Synsense.